In section 3.2, we're ready to look at our decreasing exponential functions. So we looked at primarily increasing functions in the last section. In a decreasing exponential function, we're going to talk about the decay factor, and we're going to graph those decreasing exponential functions and talk about the properties of those decreasing exponential functions when we talk about the b that goes along with them. All right, so in our situation here, we're talking about some medication, Lipitor, and there's some risk if you take it too soon, and there's still some Lipitor in the body. And so a lot of pharmacists and doctors are concerned with the half-life of medications. The half-life of Lipitor is approximately 24 hours. So if you take a full dose, what fraction of that dose is still in your body after 24 hours or after 1 day? It's got a half-life of 24 hours, so half of it's still in your body 1 day later. After 2 days, again, if you don't take any more, just that original dose, don't take any more, you still have half of it into your body. So if you had to pass a drug test for Lipitor, half of it would still be in your body 1 day later. After 2 days, your body doesn't just get rid of the rest of it. It eliminates half of it again. So after 2 days, a quarter of it is going to be left in your body. Your body can filter out half of what is there. It can't just eliminate all of it, but it filters out half of what is there. So after 2 days, a quarter of it is left. So let's fill in this chart. Initially, when you first take it, you have the full dose. 1 day later, half of it is in your body still. 2 days later, a quarter of it is in your body still. 3 days later, an eighth of it is in your body. So we're going down by a factor of 2 each time. And then a 16th would still be in your body after 4 days. So we can rewrite these as powers of 2 because powers of 2 in the denominator, I'm looking at the denominator being 2 to the first, 2 to the second, 2 to the third, and 2 to the fourth. So since these are 1/2, 1 over 2, the 2's in the bottom, I can think about it as 1/2 to the 0, 1/2 to the 1, 1/2 squared, 1/2 cubed, and 1/2 to the fourth. And if you're not sure, just double check this. Take 1/2 to the fourth in your calculator or decimals and just make sure that it is 1/16, that they should be equal to each other. The reason that they're equal is because this fourth power will distribute, and 1 to the fourth power is still 1, and 2 to the fourth power is 16. Okay, what is the practical domain of the half-life function? I'm not going to make the same mistake I made in the last section about not thinking about this in terms of continuous or discrete first before I do the practical domain. So let's make sure we've considered that, and we'll write down our practical domain. So when your body is eliminating Lipitor, say you took it at 8 a.m., and there's going to be half of it the next day at 8 a.m., it doesn't just poof away at 8 a.m. the next day. It is continually being eliminated throughout the day. If you're only halfway through the day, there's going to be more than half of it left. It'll be like 3/4 left or something like that. So this one's going to be continuous. You're constantly eliminating the Lipitor, not just at a discrete whole number only valued type situation. So we're going to use a continuous domain for our half-life function. The smallest value in that domain is going to have to be 0 because before you took the Lipitor, initially, there shouldn't be any Lipitor in your system. So you don't have anything to deal with for the -1 input. So 0 is our smallest. Now, I'm going to guess on the high end of this. After 4 days, there was still a 16th. I don't know how long it's going to take for it to fully leave your body or for you to pass a drug test, without having the Lipitor show up. But I'm going to guess a week. And so I'm going to guess 7 days to start with. Say that's probably reasonable, that it's going to be a pretty minuscule amount. And then we can look at the graph and see if this confirms our opinion. Oh. Well, they want me to draw it without using decimals, or, well, they want me to draw it without using the function. So I guess I can do that. But I'm going to use the function anyway because it's easier. I'm going to get it to autofill. So the amount of, why are they calling it Q? I don't know. But they are the amount of lipitor, they're calling it Q, in your body, it was going to be 1/2 raised to the number of days. So 1/2 raised to the T. And then we had our table that had 0, 1, 2, 3, 4. And we had our Q of X1. So if I look at the data, and I'm going to turn off my function just so I can see the dots. They were wanting me to graph just the dots. I can see the pattern right here, although I do want them connected because we are a continuous function. So I'm going to sketch what we were seeing over here, that I had a situation that looked like this. I'll just put on one more there. I don't know how many dots I had, but this is sort of what we're seeing. And so we would want to connect those. All right. All right, so we're going to go away from context now, because if we go away from context, we'll be allowed to look at the negative inputs. They'll make sense. We'll look at larger inputs, and they'll make sense. So I'm going to keep my same function here. I guess we're changing its name to G. We're changing the input to X instead of T, just because we took away the context. All right, and then we're going to add in some rows for negative numbers, -3, -2, -1, 0, 1, 2, 3, 4, 5. Perfect. So when you put -3 in, you get 8, and then 4, and then 2, and then 1, and then 0.5. We had written it before as 1/2. And 0.25, we had written it before as 1/4. And so on. We're just writing the decimal versions of these numbers right here instead of the fractional versions, which we saw on the previous page, the 1/2, 1/4, 1/16, 1/8, 1/16, and so on. 1/32 for the 5th. Okay. All right. And let's take a look at the next page. Hopefully we'll get to talk about this. Describe how you can obtain the output value for x equals 6 using the output value for x equals 5. Okay. So each of these values, if we look at the multiplicative pattern for each of these values, they are being divided by 2 each time, right? Or since we'd like to refer to this as a multiplicative pattern, we see divided by 2 because we see the division there. We want to think about the multiplicative pattern, though, what you're multiplying by. And if you're dividing by 2, you're multiplying by 1/2. So instead of thinking about what we're divided by, if we can flip that to think about what we're multiplied by, that gets us our multiplicative value, which is going to be important in determining the base of the exponential function. So we're multiplying by 1/2 each time we increase the x value by 1. It is important that these are increasing just by 1 each time, and that's going to give us the pattern right here. So what we would describe over here is we would divide the output from x equals 5 by 1/2, divide by 2, but I wanted to say multiplicative. I'd multiply by 1/2. So multiply the output by 1/2 to go from x equals 5's output to x equals 6's output. Multiply by 1/2. All right, sketch the graph. And they've given me a particular window they would like to see this graph over. -6 to 6 on x and -4 to 10 on y. All right. Okay. I can turn off my dots and just look at the shape of this graph. Let me put a couple axes in the middle real quick. I'll draw this rough shape of this graph. All right. So you can see the picture I drew as you were looking at the one on Desmos. That's basically what I tried to draw. This shape right here. And talk about its domain and its range. All right, so domain inputs, left, right. I can certainly plug negative values in. I can plug positive values in. I can plug any negative value or any positive value in. So I can plug in any real number. And for its range, for outputs, I can certainly have all the positives. I cannot get into the negatives because I'm going to be stuck right up here above the x-axis. I can't even get to 0. I'm going to be at 0 to infinity, 0 being the lowest, infinity being the highest. I have put those in order, numerical order, lowest to highest. Determine the vertical intercept. Okay, so you should be able to click on this point, or you can plug 0 into the function, and you should get 0, 1, because anything raised to the 0 power gives you 1. Is the function increasing or decreasing? As we slide down this function, it is decreasing. So just for a quick comparison with this picture and the last side, in our last section, when we saw the shape in this direction, this was our increasing shape. And this is our decreasing shape. So if we're comparing that to linear functions, we had increasing and decreasing linear functions. We have increasing and decreasing exponential functions curving upward and curving downward. Okay, so our exponential function is going to be decreasing or have a decay factor if the value of b, the base, is between 0 and 1. So the base has to be positive, but it has to be less than 1 if it's going to be a decreasing factor. The base for this one, remember, was 1/2. 1/2 is between 0 and 1, so I have my decreasing exponential function. And again, it decreases by a factor, by a multiplicative factor of b. All right, and we're going to identify our decay factors, if any. Okay, so my decay factor for this first one, base of the exponential function here is 2/7. As long as this number is a number that is smaller than 1, it's a decay factor. So my decay factor is b, and it's 2/7. The decay factor for this next one is 0.98. That's smaller than 1. It's positive, so it's a decay factor. On our next page, 1.8, that's not a decay factor. That's a growth factor, right? Because it's too big. It's bigger than 1. So it's a growth factor of b equals 1.8, but it's not decay factor. And then this one, 0.8, that's nice and small. But wait a minute, that x is not in the exponent. This is linear. So linear functions don't have decay factors. Instead, they have slopes. That's not a decay factor. It's actually an increasing. It's not even decreasing. It's an increasing exponential function because it's got a positive slope. Okay. So return to the graph of g of x equals 1/2 to the x. Does it have an x-intercept? No, it does not. It does not because, again, the graph was staying right above the x-axis. It gets really, really close, but it does not actually hit it. All right, so we're going to plug in 1, 3, 5, 7, and 10. I already have most of those values in this table, so I'm just going to add 7 and 10, the two I didn't have, and jot those down real quick. At 1, we were at 0.5. At 3, 0.125. At 5, 0.03125. At 7, 0.0078. And at 10, I have to see my exponent on that real quick. 10 to the negative 4. So 0.3 zeros, 1, 2, 3 zeros, and then 9, 8. All right, if those values seem familiar, we were getting these same kind of numbers when we had negative values plugged into our 2 to the x value. I remember this one in particular. But as the input values get larger in this function, what happens to the output values? They get smaller. But just saying smaller is not enough because smaller could mean they're decreasing, they're getting negative. Smaller means that they're getting closer to 0 here. So I need all of that part of the explanation. They're getting smaller, getting closer to 0. They're not getting smaller like -10, -11, -12. Those are getting smaller, different kind of smaller. Does the graph have a horizontal asymptote? Why, yes, it does, because it's getting closer to that x-axis again. So it's still the x-axis or the line y equals 0, however you want to phrase it. The x-axis or the line y equals 0 is the horizontal asymptote. My graph is getting closer towards it. In our increasing functions, got closer to the left side of the x-axis. It's still the same thing, though. Now we're getting closer to the right side of the x-axis. All right, now we've got a couple of functions down here where we're going to mix up increasing and decreasing. So first of all, for 1.08 to the x, the base is 1.08. That's bigger than 1, so this is a growth factor. There is no x-intercept, and the y-intercept is 0, 1. The horizontal asymptote is y equals 0, and this function, since the base is bigger than 1, is increasing. Some of these things are going to be the same for all of these. So for the next one, I'm going to do the things that are the same. Well, I guess I'll do everything, but I'm going to color code them. Okay, so the base is 0.75 for this one. That's smaller than 1, so this is a decay factor. There's still no x-intercept. The y-intercept is still 0, 1. The horizontal asymptote is still y equals 0, but this function is decreasing. So these are the same. These are different. All right, this one has a base of 3.2. That's bigger than 1, so it's got a growth factor. It has no x-intercept. It has 0, 1 as its y-intercept. It has y equals 0 as its horizontal asymptote, and it is increasing. And last, this one has 1/4 as the base. That's smaller than 1, so that's a decay factor. Because it's a decay factor, I know that we are decreasing. And then I know that it has no x-intercept. The y-intercept is 0, 1, and y equals 0 is the horizontal asymptote. So again, these b to the x functions have all of these items the same. The only difference is sometimes, depending on the base value, they're increasing and sometimes they're decreasing. I call these functions b to the x functions because all they have is a base. If I was thinking about a linear comparison, where a linear function is mx plus b, these would be like mx, where there's nothing added on to them yet. These ones are going to have, eventually, in the next section, other components. They're going to have an a and a b value. We just don't have our a yet. Right now, we're looking at functions where base is the only contributing factor so far. Oh, they wanted me to graph these. Go ahead and graph those and make sure that all this information is correct. But without graphing, how might we determine which increase or decrease? It's based on the growth or decay factor. Please feel free to graph them and make sure that this function increases and this function decreases and this function increases and this function decreases. Okay. Oh, we did this in the last section. For number 7, we're going to look at these and try to figure out if they are linear or exponential. So we're going to remember that linear are additive, exponential are multiplicative. So if I'm looking at these, I can kind of see right here that this is an increase of 3, right? And again, it's just an increase of 1 on x. It has to be a consistent increase on both. We tend to ignore the x's if they're increasing by 1, because you're just going to divide by 1. So this is linear. And it's not asking me to describe the slope, but I can. I can see the slope is 3 over 1, which is 3. I could actually do the computation just to make sure, but I can see it's got an increasing factor of 3. All right. Now, this one, 9, 3, okay, this is not subtractive or additive. It's not linear. But I can see that this pattern would be that if I go from 1 to the next, I would divide by 3. And I'm going to flip this around to what is the multiplicative pattern? That would be times 1/3, right? If I'm dividing by 3, I can multiply by 1/3. So this is exponential with a base of 1/3, decay factor of 1/3. One question left over here. Determine the decay factor represented by just the first sequence. So we have to assume this is exponential now, and then fill in the rest. Okay, so if I'm assuming this is exponential, then this is going down by a factor of 1/4 would be the factor, right? Because I can see if I take 16 down to 4 is divide by 4, and divide by 4 must mean that my multiplicative factor is 1/4. So my decay factor is going to be 1/4. If I know my decay factor is 1/4, I can take 4 times 1/4. That's 1. And I'll move decimals over here so we can get some help with the multiplications. 4 times 1/4 is 1. And if I just copy this times 1/4, I can do times 1/4 again. I'm going to keep it in fraction form. 1/4 times 1 is 1/4. And then paste another 1/4, 1/16. Oh, and I'm done. I could have kept going with that with some more multiplies by 1/4 to continue the table. One more thing before I add on to the next section here is that I had hinted that one of the ways to compute the base was by taking y2 divided by y1. You do have to be careful with this because it only works if your inputs are consecutive. My inputs here are consecutive, increasing by 1. But if I do that division directly, like if I took 4y2 divided by y1 4/16, that's another way of achieving the base value of 1/4. And I hinted at that a little bit in the last section. That the base, if you have consecutive inputs, can be determined by the ratio of consecutive outputs, of outputs for consecutive inputs. There we go.